In 2020, a faint star in the Milky Way brightened, and not by much. Not enough to see by eye, but enough for a survey telescope in California to flag it as something unusual. The star was about 12,000 light-years away, in a crowded part of the galaxy. At first, it looked like one more small transient in a sky full of them. Then astronomers looked closer. The event was too faint to be two stars merging, too dusty to be a normal flare, and just strange enough to fit a prediction astronomers had been waiting decades to see. A star eating one of its planets. That became the story in 2023. A dying star had swollen into a red giant. One of its planets had drifted too close. The planet entered the star's outer gas, lost speed, spiraled inward, and disappeared. It was a clean explanation. Maybe too clean. Because when the James Webb Space Telescope looked at the remnant 2.5 years later, it found the wrong kind of star. Not a giant. Not a swollen dying star. A small, faint star with less than a third of the sun's luminosity. And that changed the whole event. A star like that could not have swallowed a planet by swelling outward. So the planet still seems to have been destroyed, but the cause had to be something else. By the end of this video, you will understand what happened around ZTF SLRN-2020, why the original story fell apart, and why the corrected version is stranger than the headline. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. That brightening was caught by a survey camera at Palomar Observatory in Southern California. The instrument is called the Zwicky Transient Facility, ZTF for short. Every clear night, it scans huge patches of sky, looking for things that have changed. New brightenings, sudden fades, anything moving against the background of fixed stars. Most of what ZTF flags is ordinary, variable stars varying, asteroids drifting, known transients doing their usual thing. The interesting events hide inside that broader stream, and we have to sort them out by their behavior. Now picture the volume of data this generates. ZTF scans hundreds of square degrees of sky every night. It produces millions of alerts per year. Most of those alerts are quickly classified and filtered out. A small fraction, a few percent, get flagged for deeper attention. Of those, a smaller fraction still turn out to be genuinely new physical events worth long-term follow-up. So the filtering is severe. By the time something rises to the level of a candidate new transient class, it has already passed many automated and human checks. Now think about what the Discovery team actually did once ZTF SLRN-2020 cleared the early filters. They followed up with deeper imaging at multiple wavelengths. They obtained spectra to characterize the source. They cross-matched against archival catalogs to look for prior history. They built a dedicated multi-year monitoring program around this single object. The 2023 paper that announced the engulfment interpretation represented the cumulative result of all that work, not a single observation. So the headline that traveled, "A star ate a planet," was the distilled summary of years of careful follow-up, not a snap judgment. The technical content underneath that headline was substantially more nuanced than any single article could convey. ZTF SLRN-2020 was one of thousands of alerts. The brightening was modest, bright enough to flag, not bright enough to notice without a telescope. But the shape of the light curve was clean. A fast rise, a clear peak, a slow fade. That kind of pattern is unusual enough to chase. So they chased it for 3 years. When the analysis came out in Nature in 2023, the team made a strong claim. We had finally caught one. A star eating one of its planets. The first time anyone had directly observed the kind of event astronomers had been predicting for decades. The story was tidy. A red giant, an aging, swollen star at the end of its life, had expanded outward over time. A close-in planet, orbiting nearby, found itself caught inside the star's outer atmosphere. Friction with the gas slowed the planet down. The orbit decayed. The planet plunged inward. The system flashed, then it faded, then it was over. A planet had ended. Now think about what red giant evolution actually looks like physically. A sun-like star spends about 10 billion years quietly burning hydrogen in its core. During that long phase, its size and brightness barely change. Then the core hydrogen runs out, and stellar evolution moves into a faster phase. The core contracts, the shell around it ignites, the outer layers expand outward. Within a few 100 million years, fast in stellar terms, the star can swell to 100 times its earlier radius. Picture the Sun reaching outward past where Mercury orbits, past where Venus sits, possibly past Earth. The outer atmosphere becomes huge, cool, and tenuous. Its surface gravity drops to a fraction of what it used to be. The whole envelope of the star turns into a low-density, slowly moving sea of gas, extending out into space that had previously been empty. And that's the geometry the original engulfment story was built on. And here's why this story traveled so fast. We've been told for decades that this is the long-term fate of close-in planets around aging stars. The Sun will do the same thing in roughly 5 billion years. Mercury, almost certainly. Venus, very likely. Earth, possibly. The textbook diagram shows up in every introductory astronomy course. A red ball expanding outward, a small dot disappearing inside it. Now imagine the satisfaction of finally catching one of these in the act. A long-predicted cosmic process watched in real time. That was the appeal. That was what the press picked up, so the headline ran, "A star ate a planet." The diagram of an expanding red giant ran with it. But the case wasn't as clean as the headline made it sound. Look at what the energy budget said. Stellar mergers, two stars spiraling together, produce a flash that radiates the energy of millions of suns. The 2002 event V838 Monocerotis was one of those. So was V1309 Scorpio in 2008. Both of them, when they happened, lit up the sky. They were bright enough to be obvious from Earth at huge distances. They left behind dusty shells massive enough to be tracked for years. ZTF SLRN-2020 was nothing like that. Orders of magnitude fainter at peak, modest in total radiated energy, tiny by stellar merger standards. If we put it on the same scale as those bright stellar mergers, we wouldn't even see it on the chart. That faintness was a clue on its own. It said the destroyed object wasn't a second star, it was something much smaller, substellar, probably a giant planet, possibly a brown dwarf, one of those failed star objects that sit between planets and stars en masse. Either way, the energy pointed downward, into the planetary regime. So far, the story still holds together. Faint flash, small destroyed object, clean light curve, a planet eaten by a star. But here's the part that mattered, even at the time, and that didn't get much attention in the press. The whole story rested on a single assumption. The host star had to be a swollen red giant. Its atmosphere had to extend outward far enough to overlap the planet's orbit. The expansion of the star had to be the engine of the destruction. Imagine the geometry for a moment. A normal Sun-like star is roughly 1 solar radius across. That's about the size of the Sun today. A red giant, late in its life, can swell to 100 times that size. The outer atmosphere reaches out to where the inner planets used to be. A close-in planet, sitting at maybe a few % of an Earth-Sun distance, suddenly finds itself inside the star. The star reaches out, the planet is overtaken. If the host wasn't a swollen giant, the entire mechanism collapses. No atmosphere reaching out to grab the planet. No way for the star to swallow what's near it. So the question of what the host actually was becomes the question that decides everything. The team thought the host was a giant. Their spectra and modeling pointed that way. The inferred properties fit. But here's the catch. They couldn't see the host directly. The dust from the outburst was in the way. The remnant, the star left behind after the flash, was buried under warm material. They were inferring its properties indirectly, from energy balance and from how the light curve fit their model. So the story, as told, depended on something that hadn't actually been measured. Now think about how scientific reporting tends to handle that kind of caveat. The original paper was careful. It noted the inference chain, it flagged the limitations. The press coverage didn't. The version of the story that traveled was the cleanest one. A red giant swallowing a planet, caught for the first time. The technical caveats stayed in the technical sections. And none of this is criticism, that's just how these things go. We build a model, the model fits. Until something forces us to test it, we tend to assume the fit means the model is right. What forces us to test it, sometimes, is a better instrument. And there's another piece, sitting in a separate telescope's archive, that should have made everyone slow down before the headline travelled too far. A small space telescope, called NEOWISE, had been watching the same patch of sky for years before the outburst. Its job is to scan the sky in infrared light, looking for asteroids. Along the way, it builds a long-term record of how the infrared sky changes. Every star, every dusty system, every quiet source. When the team checked NEOWISE's archive for ZTF SLRN-2020, they were checking for prior history. They expected a flat baseline, a few years of nothing, then the outburst, then the fade. That isn't what they found. The infrared light from the system had begun rising about a year before the optical flash. Slowly, steadily, a long, gradual warm-up. Something was happening to the system long before the moment everyone associated with the engulfment. That single fact, hiding in NEOWISE's archive, is the first crack in the headline picture, and it's where the harder questions begin. NEOWISE is a small infrared telescope with an unglamorous job. Its main task is to find asteroids by their thermal glow. Along the way, it scans the sky in 2 infrared bands, again and again, year after year. That repetition builds something rare in astronomy, a long-term record of how the infrared sky is changing. Now think about why this kind of long-term record matters. Most telescopes operate in pointing mode. They're aimed at specific targets for specific purposes. They're not naturally building archives of the changing sky. NEOWISE, by accident of its asteroid hunting mission, does exactly that. Every patch of sky gets revisited every 6 months or so. Over years, that adds up to a multi-year baseline for everything in its field of view. So when something interesting happens in the sky and we want to know what it was doing for years before the event, NEOWISE is one of the very few places to look. When we go looking for ZTF SLRN-2020 in NEOWISE's archive, that record is what we're checking. What the team found wasn't a flat baseline. The infrared brightness of the system started to climb roughly a year before the optical flash. Smoothly, no spikes, no sudden jumps, just a steady gradual rise that built up month after month, until the visible outburst finally caught up with whatever was already happening. A year is a long time. Now think about what a sudden engulfment is supposed to look like. A planet enters a star's atmosphere, friction does its work, the orbit decays, the planet plunges, the flash happens, brightness rises, peaks, fades. The whole event plays out on a timescale of weeks to months. A year-long warm-up doesn't fit that picture. Not naturally, not as a single event. So whatever was happening to ZTF SLRN-2020 before the flash, it wasn't sudden. Something was building, and the something had to be producing infrared light, which in practice almost always means warm dust. Here's why dust matters so much in events like this. When stars or stellar systems lose mass, the lost material moves outward. It cools as it expands. Below a certain temperature, atoms can stick together into solid grains. Those grains are what we call dust. And dust does something specific. It absorbs starlight, mostly at visible and near-infrared wavelengths, and re-emits it at longer infrared wavelengths, set by the dust's temperature. So when a system glows brighter in the infrared without getting brighter in the visible, the natural reading is simple. There's more dust in the system, or the dust is hotter, or both. Now think about what an infrared signal actually carries beyond just brightness. The temperature of dust sets the wavelength at which it radiates most strongly. Cooler dust radiates at longer wavelengths. Warmer dust radiates at shorter ones. So by measuring the system's brightness at multiple infrared wavelengths, we can in principle infer not just how much dust is present, but how warm it is, and how that warmth is distributed. For the NAOI's bands specifically, the two channels are at roughly 3.4 and 4.6 microns. Both fall on the warm end of the infrared spectrum. The ratio between brightness in those two bands is sensitive to dust temperature. The way that ratio evolves over time tells us whether the dust is getting hotter, cooler, or staying the same temperature even as more of it forms. So NAOI's wasn't just measuring a single brightness number. It was building a multi-wavelength picture of how the dusty environment around ZTF SLRN-2020 was evolving over the year before the optical flash. And that's a much richer dataset than a single brightness curve would be. Now think about what dust grains are made of. The most common species in stellar outflows are silicates and carbon-rich grains. Silicates are essentially tiny rocks, microscopic versions of the same minerals that make up the Earth's crust. Carbon grains are basically soot. Both form by condensation as gas cools below the relevant solidification temperatures, around 1000 to 1500 Kelvin for silicates, somewhat lower for carbon-rich species. So when we say dust is forming around a stellar transient, we mean material is cooling enough for these microscopic grains to crystallize out of the gas. They float outward, they radiate. For ZTF SLRN-2020, the infrared rise was telling us that warm material was building up around the source for a year before anyone saw the flash. And that's a real measurement, not interpretation. NAOI's saw the brightness climb. The shape of the climb is in the archive. The timing relative to the optical flash is in the archive. None of that depends on which model we favor. What does depend on the model is what was producing the warming. Two ways to read it, both are physically reasonable. The first reading is that dust was being made. Material was being shed from the system somehow, slowly, over a long stretch. As that material moved outward, it cooled. Grains formed. The infrared signal grew because there was more dust to absorb and re-emit the central source's light. The optical flash, when it came, was the final, more violent event sitting on top of the slow build-up. The second reading is that material was being heated, not necessarily expelled. Some kind of interaction was injecting energy into existing material in the system. The energy raised the temperature of nearby gas and dust. The infrared signal rose because warm material radiates more efficiently. The optical flash in this version was a separate, later episode that finally produced the visible signature. Both readings keep the event multi-stage. Neither one fits a sudden engulfment. And here's where the problem with the original picture really starts to show. A red giant slowly expanding toward a planet does that on a timescale of millions of years. The orbital decay phase, where the planet plunges through the atmosphere, plays out in weeks at most. Between those two timescales, millions of years and a few weeks, there's a yawning gap. The infrared lead time falls awkwardly inside that gap. Too short to be slow stellar evolution, too long to be a single dynamical plunge. So the picture has to stretch. The original team handled this by extending the engulfment story. They proposed that the planet had spent that year working its way through the very outer layers of the expanding star, slowly grinding through tenuous gas, shedding material, producing dust. Then, at the end of the year, sliding into denser layers and finishing the destruction in a final, faster plunge. That picture is internally consistent. It accommodates the infrared rise, it accommodates the optical flash, it even accommodates the modest energy budget. We don't need any new physics to make it work, just a longer slow phase than the cartoon version usually shows. But notice what's still doing the heavy lifting. The host star still has to be a red giant, its outer atmosphere still has to extend out to where the planet was orbiting. Without that, the slow grind doesn't have a place to happen. The planet has nothing to grind through, so even with the lead time accommodated, the original picture's central assumption hadn't moved. The host had to be big and swollen. Now picture an alternative reading, the one that became important later. What if the host wasn't a giant at all? What if the planet wasn't being slowly chewed up by an expanding star, but was instead falling inward on its own, its orbit decaying through a different mechanism, until it grazed a small, normal-sized star's outer atmosphere? In that version, the year-long infrared rise is still consistent with material being shed and dust forming. But the geometry is reversed. The star isn't reaching outward. The planet is falling inward, so the same infrared signal can come from two very different physical setups. Both produce slowly building dust. Both produce a gradual brightness rise. Both are consistent with Neowise's archive. Both readings produce a similar infrared signal. Neowise's data alone can't tell them apart. We'd need to see the host star directly after the dust thinned to settle which version was right. That measurement was still 2.5 years away. Until then, the infrared lead time was a question with no answer. A clue that something more complicated than the cartoon version had happened. A reason to be careful about how confidently the engulfment story was being told. Look at the position the field was in. The team noted these caveats carefully in their paper. The press coverage didn't. The version that traveled was the cartoon. The version that needed checking was the technical one. And that gap between technical caveat and public confidence is where the trouble was building. Now think about why this kind of archive-driven discovery matters in modern astronomy. We take so many observations now, across so many wavelengths and at such high cadence, that almost any new event can be checked against the archived past of the same patch of sky. Neowise is one example. Time domain surveys are another. Radio archives are another. When something interesting happens, we can almost always go back and ask whether anything was happening before, and the answer surprisingly often is yes. So the modern transient era isn't just about detecting new events, it's also about reconstructing the run-up to those events from data that was already collected for other purposes. ZTF SLRN-2020 is a good example of how that kind of reconstruction can change a story before any follow-up observations are made. The infrared lead time was sitting in Neowise's archive the whole time, we just had to look. This pattern, finding pre-event signals in archival data, has reshaped how transient events are interpreted across many different categories. Supernovae sometimes show pre-explosion brightening that flags them as unusual. Tidal disruption events around supermassive black holes sometimes show subtle brightening over months before the obvious flare. Active galactic nuclei sometimes show anomalous behavior before major outbursts. The pattern is becoming familiar enough that, for any new transient class, archival pre-event data is now part of the standard analysis. So when we read about ZTF SLRN-2020 today, the year-long infrared rise isn't just a feature of this specific event, it's an example of a kind of pre-event behavior that astronomers are learning to look for systematically. Let's slow down and ask a harder question. How do we actually know ZTF SLRN-2020 wasn't just a small stellar merger? Two stars spiraling together, producing a faint flash. That would explain a lot of what we see. Why is that ruled out? The answer comes from comparing the event to systems we already understand. Two of those comparisons matter most. The first is V13009 Scorpii. In 2008, this system brightened sharply. Astronomers had been monitoring it for years before the outburst, almost by accident. They could see the binary getting tighter, the two stars closing in on each other, the orbit decaying. Then the merger happened. The system flashed, radiating the energy of thousands of suns. The flash was bright enough to be tracked from Earth without much trouble. The aftermath included a substantial dusty shell, expanding outward at characteristic speeds. Now think about what made V1309 SCO so valuable. Astronomers had years of pre-merger photometry. They could watch the orbit decay in real time. The orbital period was shrinking by tiny amounts each cycle. When the merger came, the prediction had been there. The event was the textbook confirmation that two stars in a tight binary can decay together until they fuse. So V1309 Scorpii is, in some sense, the textbook stellar merger. We watched it coming. We watched it happen, we watched it fade. The second is V838 Monocerotis in 2002. Even brighter at peak, a flash equivalent to roughly 1 million suns. The aftermath included a famous expanding light echo, dust around the system that lit up as the flash washed past, producing one of the most spectacular images Hubble ever captured. V838 Mon is what a brighter stellar merger looks like when it goes off in a neighborhood with a lot of surrounding material. Look at the difference in light echo behavior briefly. A light echo forms when a flash from a sudden brightening illuminates pre-existing dust around the system. We can see the flash propagate outward through the dust over months, almost like watching a ripple pass through a pond. V838 Mon's echo is famous because the dust around it was unusually structured, and the propagating illumination revealed nested shells of material that had been invisible before the flash. These two events, taken together, define a working class. Stellar mergers, in the regime we've studied closely, are luminous. They radiate a substantial fraction of a small supernova's energy. They leave dusty aftermaths. They do this on timescales of weeks to months. ZTF SLRN-2020 wasn't in their league. Look at the basic numbers. Peak luminosity of ZTF SLRN-2020 was orders of magnitude lower than the bright stellar mergers we know. Total radiated energy was modest, small enough that if we scaled it onto the same chart as V13009 SCO or V838 Mon, ZTF SLRN-2020 would barely show up. The light curve sat near the bottom of the dynamic range that those events define. That faintness is the first argument against a merger interpretation. Now think about what that faintness means physically. The energy released when two objects fall together is set broadly by how much orbital and accretion energy is liberated as the smaller object moves deeper into the host star's gravitational potential. Bigger object falling in, more energy; smaller object, less energy. We can flip this around. Less energy, smaller object. For ZTF SLRN-2020, the energy pointed downward, and it pointed below the energy expected for a stellar merger involving even a small companion star. We're not just below V838 Mon, we're below the kind of merger you'd get with the smallest plausible secondary star. The destroyed object had to be substellar, below the mass at which an object can sustain hydrogen fusion in its core. That's roughly 75 times the mass of Jupiter. Anything below that is not a star. So the destroyed object had to be a giant planet, a brown dwarf, or something on that scale. Now consider brown dwarfs for a moment. They're often called failed stars. They form like stars but never quite get massive enough to ignite hydrogen fusion. They glow weakly from leftover heat and from limited deuterium fusion early in their lives. They sit in mass between the largest planets and the smallest stars, with no clean line dividing them from either side. A brown dwarf falling into a star would produce a flash. It would be fainter than a stellar merger. It would still be brighter, on average, than the engulfment of a true planet. ZTF SLRN-2020 sat near the planetary end of that range, but the team couldn't pin the destroyed object's mass precisely. The energy budget gave them a rough range, somewhere between a few Jupiter masses and a few tens of Jupiter masses. Not a tight constraint, but tight enough to say substellar, tight enough to rule out a normal stellar merger. Now think briefly about how that mass range gets calculated. The total energy released depends on how much orbital and accretion energy is liberated as the destroyed object falls into the host star's gravitational potential. That energy scales with the host mass, the companion mass, and how deep the companion falls, with a major uncertainty in how efficiently that energy becomes observable light. So heavier objects falling in produce far more observable energy than lighter ones. Plug in the observed peak luminosity and the duration of the optical event, and we can back out a rough range for what mass had to be involved. That calculation has uncertainties. We have to assume something about how efficiently the gravitational energy gets converted into observable light. Different efficiency assumptions give different mass estimates. So the range is wide, but the lower bound, anywhere below the 75 Jupiter mass threshold, is fairly secure. Now look at the second argument, drawn from the dust. V1309 SCO and V838 Mon left behind dusty aftermaths with characteristic mass and geometry, substantial shells, considerable total mass, extended structure that telescopes could resolve. ZTF SLRN-2020's dust signature was different. Less massive, more compact, warmer in characteristic temperature. The shape of the dust spectrum didn't match the merger templates. It looked, instead, like a smaller scale outflow, the kind we'd expect from a less violent event involving a less massive destroyed object. Now think briefly about what dust mass differences mean physically. A bright stellar merger lifts off a substantial mass of stellar material, possibly several hundredths to several tenths of a solar mass in the brightest cases. That material expands outward, cools, and forms a massive dusty shell. The total dust mass is in the range of 1,000th of a solar mass and up. For a substellar engulfment, the available material is much less. The destroyed planet contributes its own atmosphere, which for a giant planet is a small fraction of an Earth mass. Some additional material is lifted from the host's outer layers. The combined mass that ends up as dust is correspondingly small, well below the merger range. So the dust mass we infer for ZTF SLRN-2020 is consistent with the energy budget. Both point to a substellar destroyed object. Both point downward in mass. So the dust pointed downward in mass too. Same direction the energy was pointing. The third argument came from the rate at which these things happen. Stellar mergers in our galaxy occur, very roughly, at a rate of 1 or 2 per decade, bright enough to detect with current surveys. We can estimate this rate from the events we've actually seen. Faint stellar mergers, fainter than V1309 SCO, would occur more often, but most of them would be too dim for current surveys to characterize well. Engulfments of substellar objects, on the other hand, were predicted to be far more common. Most stars host close-in giant planets at some level. Many of those planets are predicted to be slowly falling inward through tidal effects, on timescales of millions to billions of years. So at any given time, somewhere in the galaxy, an engulfment should be happening. ZTF SLRN-2020, with its modest energy and unusual aftermath, fit much better into the predicted engulfment rate than into the merger rate. It looked like a member of a much larger class, a class we'd been expecting to detect for years, but hadn't. So we're left with 3 arguments, all pointing the same way. Faint flash, compact dust, rate consistent with the engulfment population. The destroyed object was substellar. The event was almost certainly a planetary engulfment of some kind. We can say this with reasonable confidence even before getting into the trickier questions about exact mechanisms. Now think briefly about what these 3 arguments together rule out. They rule out a normal stellar merger of 2 main sequence or post-main sequence stars. They rule out a particularly violent variable star, where light curve variability without destruction is the explanation. They rule out a gamma-ray burst or other high-energy transient which would produce an entirely different spectral signature. They narrow the field, by elimination, to exactly the engulfment regime, a star receiving and destroying a smaller object that didn't have enough mass to undergo hydrogen fusion. So before we even got to Webb's host star measurement, the basic class of event was reasonably clear. ZTF SLRN-2020 was an engulfment of a substellar object. The arguments above are robust. They survive the later revision of the host star picture. They remain the firm foundation underneath everything we've worked through. What we can't say, just from these arguments, is how the engulfment happened. The energy and the dust tell us what the destroyed object was. They don't tell us whether it was destroyed by a swollen red giant reaching outward, or by a small star receiving an inspiraling planet. Both versions of the story produce substellar scale energetics. Both produce modest dust. Both fit the rate predictions. To pick between them, we need to look at the host star itself, and the host star, at this stage of the analysis, was still buried under warm dust. We couldn't see it clearly. We were inferring its properties from indirect evidence, and from the assumption that the original engulfment model was the right framework. That assumption was the weak link, and it was about to be tested directly. Let's take the original explanation seriously. Before we look at how it fell apart, we need to understand what made it work in the first place. The 2023 model wasn't sloppy. It was internally tidy. It made sense given what was known at the time. So let's walk through it carefully. The picture starts with stellar evolution. A star like the Sun spends most of its life burning hydrogen in its core. During that long phase, about 10 billion years for a Sun-mass star, its size and brightness change only slowly. Then the core hydrogen runs out. When that happens, things change quickly, in stellar terms. The core contracts. The contraction heats the surrounding shell of hydrogen. The shell starts burning faster. The energy production climbs, and the outer layers respond by expanding outward, dramatically. Now think about why the outer layers expand. As the energy production climbs, more radiation pressure pushes outward against the gas. The gas, in response, expands to a larger volume where the pressure can find equilibrium. The equilibrium configuration, for a star that's burning its hydrogen shell at higher rates, is one with a much larger outer radius and a much cooler photosphere. The star, in essence, restructures its envelope to accommodate the new energy budget, so the swelling isn't a slow, gradual drift. It's a structural readjustment. The star is finding a new equilibrium configuration that fits its new internal physics. The transition from main sequence to giant takes a few 100 million years from start to finish. That's slow on human timescales. Fast in stellar terms, given the 10 billion year main sequence lifetime that preceded it. A sun-like star, at the tip of the red giant phase, can swell to 100 times its earlier size. Imagine the sun reaching outward past where Mercury orbits, past where Venus sits, possibly past Earth. The outer atmosphere becomes huge, cool, and tenuous. Its surface gravity drops. The whole envelope of the star turns into a low-density, slowly moving sea of gas, extending out into regions that, when the star was younger, had been empty space. Now picture a planet that had been orbiting at, say, 2% of an Earth-Sun distance, close in, tightly bound, well outside the original stellar surface. As the star expands, that planet's space stops being empty. The planet finds itself embedded in, or skirting through, the star's new outer atmosphere. That was the geometric setup the Discovery team invoked. Now think about the timescales involved. The slow expansion of a sun-like star into a red giant takes hundreds of millions of years from the start of the transition to the peak of the giant phase. That's slow on human timescales, but fast in stellar terms. During this period, the star's outer radius can grow by a factor of 100. The outer atmosphere becomes huge, cool, and tenuous, with surface densities that fall to a tiny fraction of what they were on the main sequence. So the basic physics of how a star can swell out to engulf a close-in planet is well established. We've worked through it in textbooks for decades. The original engulfment story for ZTF SLRN-2020 was just applying this textbook physics to a specific system. What happens next is the in-spiral. Here's how that works. A planet moving through gas, even very thin gas, experiences drag. The gas exerts a gentle, sustained backward force on the planet. That force takes energy out of the planet's orbit. Each pass through the dense layers leaves the planet a little less energetic, a little closer in. The orbit shrinks, and here's the crucial part. Drag depends on density. The deeper the planet sinks into the star, the denser the gas around it. The denser the gas, the stronger the drag. The stronger the drag, the faster the orbit decays. So the in-spiral is not steady, it accelerates. We can think of it in two stages. A long, slow phase, where the planet is barely inside the outermost layers of the star. The orbit decays gently, maybe over a year, maybe longer. The planet gradually sheds material. Dust forms. Then a fast runaway phase. The planet has descended deep enough that drag rises sharply. Energy loss outpaces the planet's ability to resist destruction. The orbit collapses on a timescale of days to weeks. The planet is torn apart. And that's the basic engulfment cartoon. Now think about why the runaway phase is so much faster than the slow phase. As the planet descends, the surrounding gas density rises sharply. Drag forces are roughly proportional to gas density, to the square of the planet's velocity, and to the planet's cross-sectional area. So as the planet sinks into denser layers, all three terms grow. The drag force escalates rapidly. The planet's orbital energy gets dumped into the surrounding gas faster and faster. The orbit shrinks on a positive feedback loop. Eventually, the planet hits layers dense enough that it can't survive as a coherent object. Tidal forces from the host pull it apart. Whatever remains gets absorbed into the host's atmosphere, mixing into the deeper layers over time. The visible event ends with the planet effectively gone. Now look at how the 2023 team mapped this onto ZTF SLRN-2020. The slow phase in their picture was the year-long infrared lead-up. The planet was already inside the star's outer atmosphere, slowly grinding through it, shedding material that cooled and formed dust. Neowise saw that infrared rise build up over the year before the optical flash. The fast phase in their picture was the optical outburst itself. The planet had reached denser layers, the destruction ran to completion, material was thrown outward in a more violent ejection. The system flashed, it peaked, it faded. The post-outburst dust was the residue. Material lifted from the star's outer layers and from the disrupted planet, expanding outward, cooling, eventually radiating most of its energy in the infrared. Each piece of the observed timeline got a place in the model. Energy budget worked. Dust mass and temperature were broadly consistent. Light curve shape, when modeled, matched. The picture had internal logic. Each part of the data found a home. It was, on the whole, a coherent reading of the event. But here's what made it fragile. Every step of the picture depended on one thing being true. The host star had to be a swollen red giant. The atmosphere had to extend out to where the planet was orbiting. The whole geometric setup, the star reaching out to overlap the planet's orbit, had to be in place. Without that, the slow phase has no medium to grind through. The fast phase has no denser layers to plunge into. The model simply doesn't have a place for the planet to be destroyed. So the question of what kind of star sat at the center of ZTF SLRN-2020 wasn't a side question. It was the central question. The whole story stood or fell on it. The team thought the host was a giant. Their reasoning was reasonable. Now think about what they had to work with. Spectra of the source, taken before and during the outburst, showed signatures consistent with a giant atmosphere. Modeling of the brightness and color suggested a large, cool object, the kind of object you'd expect at the late stages of stellar evolution. And the model itself implied that, for the energy budget to work out, the host had to be the kind of star that could plausibly host such a process. These arguments were indirect. They depended on inference from limited data. The remnant star, the host as it sits today after the outburst, was buried under warm dust. Direct, clean observations of the host's properties would have to wait until that dust thinned, or until an instrument capable of seeing through it took a careful look. That gap mattered. When a model fits data well, it's easy to forget that the fit relied on parameter choices that haven't been directly tested. The 2023 model fit ZTF SLRN-2020 well, given the assumption that the host was a giant. The model wouldn't have fit nearly as well, in fact it wouldn't have fit at all, in the same form, if the host turned out to be something else. The fit wasn't a test of the host, the fit assumed the host. And none of this is criticism of the original analysis. That's how transient science has to be done. We build a model with the most reasonable interpretation of the available data. We say what the model implies. We note, sometimes more clearly than press coverage will retain, the assumptions on which it rests. The 2023 paper did this carefully. The host star was discussed, the observational limitations were noted, the engulfment was framed as the best current interpretation, not the only possibility. In the press, those caveats faded. The headline became, "A star ate a planet." The diagram of the swollen red giant ran in every science article about it. The story settled into the public consciousness in its cleanest form. Now think about why the cleanest version is the one that travels. A picture of a red ball expanding and swallowing a small dot is intuitive. It's easy to draw. It's easy to explain in 2 sentences. Obtuity, it connects to the existing public understanding of stellar evolution, which already includes the textbook image of an aging sun expanding past Earth's orbit. So the story slotted neatly into a mental model that was already there. The technical caveats, the inferred host, the indirect modeling, the gap between data and assumption, required several extra paragraphs of explanation that wouldn't fit in a headline or a press summary. So the cleanest version traveled because it was the version that fit the available column inches. The technical version, more careful but more demanding of the reader's patience, stayed inside the academic literature. That asymmetry is normal. It's just worth recognizing that when a popular story about a recent finding feels too clean, it often is. And then Webb came online, and it turned its instruments on the source. And the assumption that had been holding the engulfment model together was tested directly for the first time. What Webb measured is the moment the original picture broke. Almost 2.5 years after the optical peak, the James Webb Space Telescope turned its instruments on ZTF SLRN-2020. By that point, the warm dust had spread, cooled, and partially thinned. The light from the underlying remnant star was starting to leak out from behind it. The dust was no longer fully drowning the source. Webb is, among other things, an exceptional infrared observatory. It can pierce dust that earlier instruments couldn't see through. It can resolve faint sources near brighter ones. It can take spectra detailed enough to pull apart individual molecular signatures. For a system like ZTF SLRN-2020, where the central star had been hidden under warm material since the outburst, Webb had the right tools at the right time. The team used two of Webb's instruments, the near-infrared spectrograph called NAISPEC, which works at wavelengths from about 1 to 5 microns, and the mid-infrared instrument called MIRI, which works from about 5 to 28 microns. Together, those two instruments cover the wavelengths where both the underlying stellar light and the surrounding warm dust live. So they pointed Webb at the system and they measured. Now think briefly about what we mean by measuring a star's luminosity from a Webb observation. Webb captures the spectral energy distribution of the source, its brightness as a function of wavelength, across its operating range. With a known distance to the source, that spectral energy distribution can be integrated to give the total energy output, the bolometric luminosity. The distance is estimated independently from spectroscopic methods and from the source's location in the galaxy. The integration accounts for both the central star's contribution and the surrounding dust and gas. So the luminosity number isn't a guess. It's a multi-step measurement chain, with each step grounded in well-established astrophysical methods. For ZTF SLRN-2020, that chain converged on a small, secure value. What Webb found, when it looked at the inner part of the system, was a star that did not match the engulfment picture. The remnant had a bolometric luminosity, its total energy output across all wavelengths, of roughly 0.29 solar luminosities, less than a third the brightness of the Sun. That number is small. That number is the center of the entire reversal. Now think about what a swollen red giant capable of swallowing a planet through atmospheric expansion would have to look like. It would have to be enormous in radius. Its outer atmosphere would have to extend out to where the planet was orbiting. Its surface gravity would be very low. Its photospheric temperature would be cool. The combination of all those properties produces a luminosity hundreds of times the value Webb measured, hundreds of times higher. This isn't a fine-tuning problem. It's not a small discrepancy that could be papered over with a different reading of the data. It's the difference between two qualitatively different stages of stellar evolution. A red giant near the end of its life versus a younger star still nearer the beginning. Webb wasn't looking at a red giant. It was looking at something much smaller. The full set of measurements pointed to a star with roughly 0.7 times the mass of the Sun, classified as a K-type star, sitting close to the main sequence, the long phase where stars spend most of their lives quietly burning hydrogen in their cores. A K-type star, at 0.29 solar luminosities, is small, cool, and largely quiet. It's not in the swollen phase. Its outer layers are still tightly bound. Its photosphere sits at the radius set by main sequence physics, not by the dramatic expansion of late-stage stellar evolution. Now think about what K-type means in concrete terms. The spectral classification system runs O, B, A, F, G, K, M, from hottest to coolest. The Sun is a G-type star. K-types are slightly cooler, slightly less massive, slightly smaller, slightly less luminous. They burn their hydrogen more slowly than the Sun. Their main sequence lifetimes can run 20 to 30 billion years, much longer than the current age of the universe. So a K-type star sitting near the main sequence is by stellar standards very young in evolutionary terms. Picture a star with about 70% of the Sun's mass, 60% of the Sun's diameter, and a third of its luminosity. Surface temperature around 4,000 to 5,000 Kelvin. The kind of star that, if you placed it where the Sun is, would still warm Earth orbit distance worlds, but with a redder, dimmer light than what we see now. And that's what Webb saw at the center of ZTF SLRN-2020. There's no path from this kind of star to the geometry the original engulfment scenario required. So we have a problem, a real one. The original story said, the star expanded, the planet was overtaken, The destruction proceeded inside the swollen atmosphere. None of that mechanism is available if the host is small. The expanding atmosphere doesn't exist. The geometric setup that brought the planet into the danger zone isn't there. So the engulfment by expansion scenario, as originally described, simply cannot apply to this system. And that's a structural break, not a tuning issue. Now we have to be careful about what Webb did and didn't show. What Webb did show: the host star is small, much smaller than the original model required. The geometry of the original picture isn't possible. What Webb didn't show: that no engulfment occurred at all. The dust is still there. The infrared lead-up is still in NEOWISE's archive. The optical outburst still happened. Some kind of disruptive event clearly took place. That part of the story didn't disappear when Webb measured the remnant. What Webb did was eliminate one specific scenario, the swollen red giant version, for how that disruption happened. It didn't eliminate the disruption itself, so the planet very likely was still destroyed. We just need a different mechanism for how it got destroyed. Here's where the field had to do real work. If the host is small and main sequence-like, then the planet wasn't overtaken by an expanding star. The star wasn't reaching outward. That means the planet must have arrived at the star by a different route. The planet's orbit must have decayed. The planet must have moved inward on its own until it was close enough to interact with the host's outer atmosphere. That's a fundamentally different scenario. The geometry is reversed. In the original story, the star reaches out to the planet. In the new story, the planet falls in toward the star. Same endpoint, destruction. Different path. We'll come to the details of that new picture once we've looked at the wreckage Webb actually measured, because the wreckage is what any new mechanism has to fit. And here's something worth holding in mind. This kind of revision in transient science isn't unusual. An event is detected. A first explanation is proposed. Later observations, often with better instruments, refine or replace the first explanation. The category of phenomenon usually survives the revision. The specific mechanism within that category often doesn't. Look at the position the field was in. They had a clean confirmation of a long-predicted process, written up in Nature, covered by the press as the first direct sighting of stellar engulfment. Then a single instrument, looking at the same system 2 years later, returned a number that broke the central mechanism of the explanation. So they did what good science is supposed to do. They updated. Now think about what that update actually involved in practice. Multiple papers reanalyzed the original ZTF data with the new host star constraint in hand. The earlier light curve modeling, which had assumed a giant atmosphere, had to be redone for a small main sequence atmosphere. The dust temperature and structure had to be reinterpreted in the new geometry. The energy budget had to be checked against the new picture. None of this was trivial. It took months of additional work distributed across multiple groups. So the technical literature absorbed the revision in stages. New papers cited Webb's measurement and walked through the implications. Modeling work explored how the new geometry could reproduce the observed wreckage. The field, internally, moved on from the original interpretation. The headline didn't update so easily. The cleanest version of the story, the swollen red giant overtaking a smaller world, had become the public memory of the event. Even now, when you search for ZTF SLRN-2020, you'll find diagrams of expanding red giants. The corrected picture, which is harder to draw and harder to summarize, hasn't fully replaced the original. Now think briefly about what the corrected picture would actually look like in a single image. You'd want to show a small, dim K-type star sitting at the center, with a planet on a slowly inspiraling orbit, with material being shed during the grazing phase, with the eventual plunge, and with the layered wreckage that follows. That's much harder to capture in one frame than the simple red ball eats dot picture. The cleanest illustration of the corrected story doesn't exist as a single image yet. It exists across multiple stages, multiple timescales, and multiple kinds of evidence. So part of why the original picture lingers is that the corrected one resists single-frame summary. The cleanest version is the one that fits in a thumbnail. The accurate version requires a sequence, but within the technical literature, the assumption was gone. The original mechanism didn't survive its first real test. What replaced it had to make sense of the same wreckage with a different geometry. Same dust, same molecular gas, same energy budget, same long timescales. But now around a small star, not a swollen one. The way that wreckage was produced had to be rebuilt under those new constraints. Now think about what kind of update we're describing. The original interpretation isn't being thrown out wholesale. The basic claim that a planetary engulfment occurred is being preserved. What's being changed is the specific mechanism. The destroyed object is still a planet. The destroying agent is still the host star. The geometry of how the destruction occurred is different from the cleanest version, but the destruction itself is preserved. So the revision is structural, not foundational. It changes how the engulfment happened, not whether it happened. That distinction matters when we try to communicate what's actually been learned from this single event. The wreckage itself, when we look at it carefully, is the next clue in the rebuild. Webb did more than measure the host star. It also took the most detailed look so far at what surrounded it. The dust, the gas, the aftermath material that the outburst had left behind. That structure, it turns out, has two distinct components. They sit at very different temperatures. They occupy different regions of space, and both have to be explained by any working model of what happened. Let's look at them one at a time. The first component is the warm dust. Webb measured a temperature of roughly 720 Kelvin in the outer envelope of the system. That's hot in everyday terms, cool by stellar standards. It's consistent with grains warmed by the residual light of the central star, sitting at a distance where they neither freeze out nor evaporate. Picture it like an outer shell, not uniform, probably clumpy, carrying signatures that suggest more than one phase of formation, with hints of an even cooler component sitting farther out. Material that may have been released earlier, expanded more, and cooled more. The second component is the part that really demands explanation. Closer to the star, in a compact region the dust doesn't fully obscure, Webb found molecular gas at much higher temperatures. Hot, dense, rich in carbon monoxide. Now picture both components in the same field. Outer warm dust at 720 Kelvin. Inner hot molecular gas, much closer to the star, at considerably higher temperatures. Two distinct regions, two distinct temperatures, two distinct stories about when the material got there. This isn't what a single, fast event leaves behind. Here's why. A single short event, a planet plunging into a star and being destroyed in days, would tend to produce one shell of debris, material released more or less at once, expanding outward together, cooling with time, forming a roughly uniform aftermath. What Webb saw isn't uniform, it's stratified. Outer dust is one layer. Inner hot gas is another. There's a hint of a third, even cooler layer farther out, possibly older still. That kind of stratification points to a layered process, material released at different times, expanding to different distances, cooling to different temperatures. The destruction wasn't a single instant, it was a sequence. So now we have a real constraint on the mechanism. Whatever mechanism produced ZTF SLRN-2020 has to release material in stages, some of it early, slowly, over months. That material now sits in the outer dust layer, some of it later, more violently. That material is now in the warmer inner regions, some of it possibly even later, or maybe falling back toward the star after being thrown out. That material is the hot inner molecular gas. A single fast plunge can't do this. We need stages. Now let's look more closely at what the carbon monoxide is telling us. CO is one of the most useful molecules in astrophysical observation. It forms readily wherever carbon and oxygen are both available. Its rotational and vibrational transitions produce sharp spectral lines that Webb can resolve cleanly. The strength and width of those lines carry information about temperature, density, and motion. Now think about what CO tells us specifically. In a molecular gas, individual molecules can rotate and vibrate. Each rotational state has a slightly different energy. When a molecule transitions between rotational states, it emits or absorbs a photon of a specific wavelength. Webb can see those photons. The relative strengths of the lines tell us how the molecules are distributed across the rotational ladder, which tells us the gas temperature. The widths of the lines tell us how the molecules are moving, So a high-resolution Webb spectrum of CO carries quantitative information about the conditions of the gas, temperature, density, motion, directly. Hot CO sitting close to a stellar remnant, in a system that just produced a long transient and a structured dust shell, is a sign of recent material. Gas that was released or thrown around in the recent past, and hasn't had time to disperse or settle. That's the inner half of the wreckage, material from late in the event, possibly including some that was thrown outward and then fell back inward toward the star. The dust grains in the outer envelope are doing different work. They condensed from gaseous material that cooled below the dust formation temperature. Different chemical species condense at different temperatures. Silicates higher, carbon-rich grains lower, various exotic species in between. The 720 Kelvin equilibrium of the warm dust corresponds to material that's already condensed, and is now sitting at a distance where the residual stellar radiation keeps it at that temperature. Now look at the geometry implied by the 720 Kelvin temperature. Dust at that temperature, around a Mete-29 solar luminosity central source, would naturally sit at a specific physical distance from the star, set by the balance between absorbed and emitted radiation. We can estimate that distance from straightforward radiative equilibrium calculations. It comes out to a few times the size of the host star, possibly larger. That puts the warm dust well outside the host's photosphere. Material that was lifted out of the system during the active phase of the event expanded to the radiative equilibrium distance and is now sitting there, glowing in the infrared. Cooler material, if present farther out, would radiate at longer wavelengths and lower intensities. Hotter material, if present closer in, would radiate at shorter wavelengths and might overlap with the gas phase signatures from the inner region. Webb sees both kinds of overlap, faintly, which is consistent with a layered structure where boundaries are not perfectly sharp. Here's something else worth flagging, briefly. Some discussion in the literature has touched on possible exotic species in the spectrum, including phosphine. We should treat that very cautiously. The relevant lines are blended with other features. The conditions under which phosphine would be expected to form in the wreckage of a planetary engulfment aren't well established. Treat it as an open question. The central story of the wreckage doesn't depend on it. Now think more broadly about what we're learning to read from wreckage like this. Each new observation of post-engulfment material teaches us a bit more about how to interpret similar future events. The relative strengths of different molecular species, the temperature gradients between inner gas and outer dust, the total mass budget. Each of these will become a diagnostic tool as more events accumulate. So Webb's observation of ZTF SLRN-2020 isn't just a one-time forensic measurement. It's also a calibration, a worked example of what an in-spiral and plunge wreckage looks like at the post-event stage. Future events will be compared to this template. Differences and similarities will tell us about the diversity of the underlying process. What does matter for the rebuilt mechanism is the basic structure: hot, compact gas near the star, warmer and more diffuse dust around it, hints of even cooler material farther out, stratified by distance, stratified by temperature, stratified by time of release. So if we read the geometry of the wreckage as a chronology, a story falls out almost on its own. Material released earliest sits farthest out and is coolest. Material released later sits closer in and is warmer. Material released last is the hot inner molecular gas, possibly mixed with material that fell back inward at the end of the event. The wreckage is a record, the geometry is the timeline. Now think briefly about how rare it is, in astrophysics, to have access to this kind of layered record. Most stellar transients fade quickly enough that the post-event wreckage is hard to study in detail. ZTF SLRN-2020 is unusual because the wreckage is bright enough, recent enough, and accessible enough that we can resolve its structure with current instruments. That's an accident of timing, the right instrument coming online at the right moment after the right event. Future events caught at similar stages will be analyzed against the template ZTF SLRN-2020 has helped establish. So Webb's observations of the wreckage aren't just about this one event. They're also a calibration for how to read post-engulfment wreckage in general. That makes the data more valuable than its single event applications would suggest. Reading that timeline carefully is how we start to rebuild what physically happened. And it's the constraint that the new model, the planet falls inward picture, has to fit. Now look at what the dust spectrum, taken in detail, can tell us beyond just temperature. Webb's dust observation isn't a single number, it's a spectrum across many wavelengths, and the shape of that spectrum carries information about grain composition. Silicate grains have distinctive spectral features. Carbon-rich grains have different ones. Mixtures of compositions produce mixed spectra. By comparing the observed dust spectrum to known mineralogical libraries, we can in principle constrain what kind of material was lifted out of the system. For ZTF SLRN-2020, the dust spectral features are broadly consistent with silicate-dominated grains. That's not surprising. Silicates are the most common dust species in stellar outflows, but the details of the silicate features, exactly which mineralogical species are dominant, how crystalline versus amorphous they are, provide additional information about the conditions under which the dust formed. So beyond just temperature, the dust spectrum is telling us something about the chemistry of the destruction. Material was lifted from a planetary atmosphere, from a stellar atmosphere, or from both. The mixing of those two reservoirs, in the right proportions, produced the dust signatures we now see. Look at the work this layered reading does. It accommodates the year-long infrared rise that NEOIs caught. Material being shed slowly, early in the event, would be the source of the outer dust we're seeing now. It accommodates the optical flash. A more violent ejection later in the event produces the warmer dust closer in, and it accommodates the hot inner gas. Material from the very end of the event, plus some that may have fallen back, produces the compact CO signature. A coherent reconstruction has to do all of this with a single mechanism running across the whole timeline. The new mechanism, the planet falling inward toward a small main sequence star, does this. The original mechanism, the star reaching outward to engulf the planet, does not, given what Webb measured about the host. That's why the reading of the wreckage forces the same conclusion as the host star measurement. The geometry is reversed from the original story. The destruction is real. The agent of destruction is different. Now we're ready to look at the new mechanism in detail. If the host is a small near main sequence star, then we need to ask how the planet got close enough to be destroyed in the first place. The answer involves a process we know reasonably well from other systems. A close-in giant planet, orbiting a star like this, can lose orbital energy slowly over time. Tidal interactions with the host gradually drain energy from the orbit. The orbit tightens, the planet moves inward. On a long enough timescale, that in-spiral can carry the planet all the way to destruction. This isn't speculative physics. We've actually watched it start to happen in other systems. Look at WASP-12b, the most studied example. It's a hot Jupiter, a giant planet in a tight orbit around a star roughly Sun-like. Astronomers have been timing its orbit for years. The orbit is decaying. Each year the planet completes its orbit a few milliseconds earlier than the year before. That tiny shift, accumulated over decades, points to a tidal in-spiral that will eventually carry the planet into the star itself. The estimated time to destruction is a few million years, so we have direct measurements of orbital decay in one specific hot Jupiter. The mechanism is real. Now think about how tidal decay actually works. A close-in planet raises tidal bulges in its host star, small distortions in the star's shape caused by the planet's gravity. The bulges are not perfectly aligned with the planet's instantaneous position. Friction inside the star tends to drag the bulges slightly behind the planet's motion. That misalignment exerts a small backward torque on the planet's orbit. Each orbit, a tiny amount of orbital energy gets transferred from the planet's motion into heat in the host star's interior. The orbit shrinks. The process continues. Over millions to billions of years, a close-in planet can spiral all the way in. So tidal decay isn't theoretical. It's a measured process. The strength of the decay depends on how strongly the planet couples to the host through tidal forces, which in turn depends on the host's internal structure. Different stars, with different convective zones and different damping properties, drain orbital energy at different rates. WASP-12b is decaying fast by hot Jupiter standards. Other hot Jupiters around comparable stars are probably decaying too, just at slower rates that we haven't yet been able to measure directly. Now let's apply that to ZTF SLRN-2020. Picture the system the way it must have looked for a very long time before the event. A small K-type star sitting quietly. A close-in giant planet orbiting in a tight orbit. The planet's orbit slowly decaying, tidal forces pulling energy out. The orbit gradually shrinking year after year on a timescale of millions to billions of years. And that's the long phase. It's invisible. We can't see it directly. But it has to have happened, given what we now know about the host star. At some point in that long-in spiral, the orbit gets tight enough that the planet starts to interact with the host's outer atmosphere. That's the transition point. A planet skimming the very outermost layers of the star, where the gas density is low but not zero. Here's where the slow phase shifts into something different. When the planet starts grazing the star's atmosphere, drag from the gas adds a new energy loss mechanism on top of the tidal decay. The orbit decays faster. The planet sinks deeper into the upper atmosphere on each orbit. Tidal forces start deforming the planet itself. Material from the planet's outer envelope can be lifted off, either by direct ablation or by tidal stripping. That's the grazing phase. And in the new model, this grazing phase is what produced the year-long infrared rise that NOIs saw. Now we're connecting two things that previously felt unrelated. The infrared lead-up and the long, slow stage of the inspiral. They become the same phase, just described in different language. Material is being shed from the planet during the grazing. Some of it is also being lifted from the host's outer atmosphere as the planet plows through. The combined material moves outward. It cools. Dust forms. The infrared brightness of the system rises gradually over months as more dust accumulates. And all of this is happening before any optical flash. Because the grazing phase is, by stellar transient standards, gentle. There's not enough energy being released yet to produce a visible outburst. Just enough to disturb material and heat it. Then the orbit decays past a threshold. Beyond that threshold, drag dominates. The orbital decay accelerates sharply. The planet plunges deeper into denser layers of the star. Energy is dumped into the host on a much shorter timescale. Material is shed in a more violent ejection. The system flashes. And that's the optical outburst. So the timeline we couldn't fit into a single fast event now fits into a multi-stage one. Long invisible orbital decay, year-long grazing phase, short final plunge. Each stage produces its own observable on its own timescale. Worth pausing on what this picture preserves and what it changes. What it preserves: the planet was destroyed, the system flashed, dust formed, material was ejected. The wreckage we see now is the residue of all this. What it changes: who comes to whom. In the original story, the star expanded outward and overtook the planet's orbit. In the new story, the star sits where it has always sat. The planet's orbit decays inward over a long stretch of the system's history. The destruction happens because the planet finally arrives at the star, not because the star reaches out to it. Same destruction, opposite direction. That reversal matters for more than just the imagery. In the original story, the timing of the destruction was set by the star's evolution. The planet would be consumed when the star reached the right radius, regardless of the planet's properties. In the new story, the timing is set by the planet's orbital decay. The destruction occurs when the planet's orbit, after a long spiral, reaches the host atmosphere. Different planets, around stars of similar mass, would be consumed at different times. It depends on their initial separations and how strongly they couple to the host through tidal forces. The destruction, in other words, is now driven from the planet's side, not the star's. This has consequences for how we'll find more events like this in the future. If most planetary engulfments around solar-type stars proceed by orbital decay rather than stellar expansion, then the population of detected events will look different from what the simplest scenario would predict. The events will tend to involve hot Jupiters, not all close-in planets. They'll occur around stars at various stages of evolution, not just stars at the tip of the giant branch. The signatures will tend to involve long infrared lead-ups, not sudden onsets. Those are testable predictions. Future surveys can check them. Now think about the kinds of things future surveys will be looking for. A long infrared lead-up, like the one NEOWISE caught for ZTF SLRN-2020, would be a distinctive signature. If we can monitor the infrared sky for slow rises that precede optical transients, we can flag potential engulfment candidates before the peak. Webb-class instruments can then be ready to follow up rapidly, capturing both the active phase and the cooldown phase in higher detail than was possible for ZTF SLRN-2020. So we should be able to do better with future events. Earlier flagging, better instrumental coverage during the active phase, more direct measurements of the host while material is still being shed, a clearer reading in real time of which physical mechanism is producing the visible event. ZTF SLRN-2020 had to be reconstructed after the fact, with limited active phase data. Future events should give us the chance to read the destruction as it happens. Now look at the broader population of hot Jupiters. We've discovered hundreds of giant planets in tight orbits around their host stars. Many of them sit at orbital distances where tidal coupling to the host should be slowly draining their orbital energy. We can estimate, statistically, how many of them are likely to be destroyed by in-spiral within the next few million years. That estimate isn't sharp. It depends on the host star's tidal dissipation properties, which aren't well measured. But the broad picture is that orbital decay should be common, and in-spiral-driven engulfments should be a regular feature of close-in giant planet evolution. So the new picture isn't just an alternative reading of one event. It's a prediction that this kind of event should happen often. ZTF SLRN-2020 is, in that reading, an early example of a process that should turn out to be widespread once we know how to detect it. But here's what's not yet directly observed in the new picture: the grazing phase itself. Webb didn't watch a planet skim a star. The grazing phase, as a label, is a description of what the new model says was happening during the year when the infrared was rising. The model fits the data, but the data alone doesn't single out grazing as the only possible explanation. Other slow build-up mechanisms, different kinds of outflows, irregular mass loss, structurally different processes, could in principle produce some of the same signals. So the grazing phase is the cleanest current fit. It's not yet uniquely determined. Now think briefly about what would settle the grazing phase interpretation more firmly. Higher cadence infrared photometry during the year-long lead-up of a future similar event would help. Spectroscopy capturing material at the grazing radius, while the planet is still skimming the host atmosphere, would help even more. Direct dynamical measurements of an in-spiraling close-in planet, captured before destruction, would settle the case definitively. Each of those measurements is technically achievable with current or near-future instruments. We just need the right event at the right time, with appropriate observation programs ready to act. ZTF SLRN-2020 happened before such programs were fully in place. The next similar event, detected with Rubin and followed up rapidly with Webb-class infrared spectroscopy, should give us a much sharper view of the grazing phase. And here's an important distinction in the careful reading of the event. The host star measurement is direct and decisive. The wreckage measurements are direct. The grazing phase interpretation is model-based, suggested by the timing pattern but not yet imaged. We're being honest about which parts of the rebuilt picture are anchored in measurement and which are anchored in inference. The picture, taken whole, fits the data better than the original story did. The host star measurement is satisfied. The infrared timeline is accommodated. The optical flash has a place. The wreckage structure has a mechanism that produces it. What's left to deal with is one residual problem. The optical event lasted a long time, longer than a single fast plunge can naturally power. So there's still a piece of the puzzle that needs additional mechanisms to explain. That residual is the next constraint to work through. Here's the loose end the new picture has to deal with. The optical event of ZTF SLRN-2020 didn't fade in days. It faded over roughly 100 days. And that's a long time. too long to be powered by a single brief dynamical plunge. A runaway final plunge releases its energy fast, days to weeks at most, not nearly enough to keep a system bright for 100 days. So if the new model is going to fully explain the event, it needs to account for the long tail somehow. This kind of mismatch shows up often in transient astrophysics. When an event lasts longer than a simple single energy source's picture would predict, the usual response is to ask whether more than one process is contributing to the luminosity. Either the source is more sustained than first thought, or there are multiple sources, or the energy is being released into a structure that radiates it slowly, even though it was deposited quickly. For ZTF SLRN-2020, more than one of these probably applies. Let's go through the candidates. The first possibility is that the destruction is genuinely staged in a way that releases energy over a longer time. Some refined versions of the in-spiral model have the grazing phase produce significant mass loss in its own right, with energetic outflows that can persist for months. Material moving outward at high speeds can interact with surrounding gas and dust. That interaction can radiate. The radiation, especially if it's energetic enough to ionize and shock the surrounding material, can provide a sustained source of luminosity. So part of the long tail might come from the outflow continuing to radiate after the main plunge is over. The second possibility involves the host star itself. When a planet plunges into a star, energy is dumped into the host. Some of that energy goes into kinetic motion of the host's outer layers. Some goes into heat. The result in some models is that the star's outer layers expand briefly and become hotter and brighter than they would normally be. Now picture an inflated stellar envelope, brighter than the underlying star, slowly contracting back toward equilibrium as it radiates away its excess heat. The contraction takes time, possibly weeks, possibly months. During that time, the system shines more brightly than its quiet luminosity, contributing to the slow fade of the optical event. This mechanism is reasonably familiar. Stars that receive sudden injections of energy into their outer layers do expand and contract on these kinds of timescales. The match between the contraction time and the observed duration is one reason this mechanism has been a serious candidate. Now think briefly about why the contraction takes that long. The envelope's response time is set by the time it takes for radiation to leak out through the star's outer layers. That timescale, for a Sun-like star, runs from days to months depending on how deep the energy injection penetrates. A modest injection into the very outer layers contracts back fast. A deeper injection takes longer to relax. The time we observe, roughly 100 days, fits naturally into the range that intermediate depth injections produce. So the inflated envelope picture isn't just plausible, it's quantitatively consistent with the observed timescale. The third possibility is the dust itself. As warm dust forms and expands outward from the central source, it intercepts radiation from the star. The dust absorbs the radiation, gets heated, and re-emits it in the infrared. The re-emitted radiation has a different spectrum and a different time profile from the original. In some configurations, this dust reprocessing can extend the apparent duration of an event. Light from the early outburst gets absorbed by forming dust and is then re-emitted more slowly. The total light output of the system, integrated across all wavelengths, can therefore appear to last longer than the underlying source's intrinsic emission would suggest. We see this kind of dust reprocessing in supernova light curves. We see it in some other transient classes too. It's not unusual. So we have three candidate mechanisms: outflow continuing to radiate, inflated host envelope contracting, dust reprocessing. The most plausible reading is that more than one of them is at work simultaneously. Now think about what it means to model multiple overlapping mechanisms quantitatively. Each mechanism contributes its own light curve, its own brightness as a function of time. The combined light curve is the sum of those individual contributions. Different relative weightings produce different combined curves. By fitting the actual observed light curve, modelers can estimate the relative importance of each mechanism. The fit isn't always unique. Different combinations can sometimes produce similar overall curves. But the broad shape of the answer, that more than one process is contributing, is robust. For ZTF SLRN-2020, the long tail seems to require all three contributions in some proportion. The exact proportions are still under refinement. The basic structure of the fit, with multiple overlapping contributions, is firmly established. So this is what active modeling work on ZTF SLRN-2020 looks like in practice. Not a single clean answer, but a careful exploration of how different combinations of mechanisms can fit the observed data, with continuing refinement as additional observations become available. A pure single plunge model doesn't fit the long tail. A grazing outflow plus an inflated envelope plus dust reprocessing layered together can produce a transient lasting 100 days while still being driven, fundamentally, by the inspiral and destruction of a single planet. Now think about what this layered picture tells us about the destruction process more broadly. A single plunge event would be brief, sharp, and self-contained. The energy released would track tightly with the duration. The wreckage would be relatively simple. By contrast, a layered destruction, grazing, plunge, post-plunge envelope response, post-plunge outflow, dust formation, produces an event with extended structure across multiple timescales. The duration of the visible event becomes a record of how the destruction unfolded, not just of when it happened. So when we look at ZTF SLRN-2020's 100-day fade, we're seeing more than just the death of a planet. We're seeing the layered architecture of that death. The grazing, the plunge, the response of the host, the formation and reprocessing of dust. Each phase contributes to the visible event in its own way. Reading the light curve carefully is reading the chronology of the destruction. Now here's an important thing to be clear about. None of this is a return to doubt about the engulfment picture. The work to extend the model is refinement, not retreat. The basic claim that a planet was destroyed isn't in question. The question is how to account for all the details of the visible aftermath within the inspiral framework. That distinction matters because it's easy to read the existence of unresolved modeling questions as a sign that the underlying scenario is shaky. It's not. The underlying scenario, a planet inspiraling into a small main sequence star, is robust. The wreckage, the luminosity, the dust, the host star measurement, the timeline, all of these point the same way. What's still being worked out is the detailed energy accounting of the long tail. That's a smaller question, a refinement question. The same kind of distinction applies in many areas of astrophysics. The basic outline of how stars produce energy through nuclear fusion has been settled for decades, but the detailed modeling of what happens in the convective layers near the surface is an ongoing field of work. The basic outline of how planets form in protoplanetary disks is well established, but the specific mechanisms of giant planet formation are still being refined. In each case, ongoing modeling work doesn't undermine the basic picture. It sharpens the edges of the picture in ways that allow the next generation of observations to be interpreted more cleanly. ZTF SLRN-2020 sits in the same kind of position. Basic event, planetary inspiral and destruction. Detailed mechanics of the long tail, under refinement. Both can be true at the same time without contradiction. Now think about the broader pattern this fits into. Transients in astrophysics often last longer than a simple single energy source's picture would predict. Many supernovae have light curves that decay more slowly than a single explosion would predict, because radioactive decay of synthesized elements provides sustained luminosity over weeks to months. Some tidal disruption events around supermassive black holes show extended emission as accretion of disrupted stellar material continues long after the initial disruption. The pattern is consistent. Long transients usually mean more than one process is contributing. Now look at how this generalizes. Whenever we see an event lasting longer than the simplest version of its mechanism would predict, we should expect to find that the simplest version is incomplete. The energy is being deposited into a structure that radiates it over an extended time, or multiple processes are contributing in parallel. Or material is interacting with surroundings on extended timescales. The detailed accounting takes work, but the broad pattern is well established across transient classes. So when we see ZTF SLRN-2020's 100-day fade and ask why it doesn't match a single plunge prediction, we're asking the same kind of question astronomers ask about other transient classes. The answer involves multiple processes overlapping, each contributing on its own timescale, all adding up to the observed light curve. ZTF SLRN-2020 fits that pattern. Its long duration isn't an anomaly to be explained away, it's a feature of the kind of event a planetary in-spiral produces. And it tells us about the structure of the destruction in addition to the fact that destruction occurred. So when we look at the 100-day fade, we should read it as a record of multiple physical processes overlapping. Mass loss continuing, envelope contracting, dust reprocessing, all running together on overlapping timescales, all contributing to the slow fade. That's what's happening at the back end of the event. And it fits comfortably inside the new picture, even though it took some additional modeling work to pin down. Now we have all the pieces we need to put the full sequence together. Long invisible in spiral, year-long grazing phase, brief plunge, long tail of outflow, inflated envelope contraction, and dust reprocessing. The whole event, end to end, with confidence levels for each step. That's the rebuild we can finally lay out clearly. Let's lay out the full event from start to finish, carefully, with confidence levels for each stage, and that's the rebuild. The version of ZTF SLRN-2020 that the field now defends, given everything we've worked through, we'll go through it stage by stage, and for each stage we'll mark whether it's anchored in direct measurement or in physical modeling. Now start with the long invisible in spiral. A giant planet, roughly Jupiter mass to several Jupiter masses, has been orbiting close to a 0.7 solar mass K-type star for a very long time, probably millions to billions of years. Over that stretch, the planet's orbit has been slowly decaying. The mechanism is tidal interaction with the host. Each orbit, a tiny amount of energy is transferred from the planet's motion into the star's interior. The orbit shrinks by a tiny amount. And here's the honest accounting. We can't see this phase directly for this specific system. The only way we can argue it happened is by analogy with other systems where similar decay is directly measured, like WASP-12b, and by inference from the new picture as a whole. If the planet ended up close enough to the star to be destroyed, and if the host isn't the kind of star that would have engulfed it through expansion, then orbital decay over an extended past has to have happened. So this stage is physically required, but not directly observed. Now move to the transition. The planet's orbit decays into the regime where the upper atmosphere of the host becomes relevant. Drag from the stellar gas adds a new energy loss mechanism on top of tidal decay. The orbital decay accelerates. The planet starts to graze the outer layers of the host. We're at the start of the year-long lead-up, and here's where we're firmly in model-based territory. The grazing phase is the cleanest interpretation of the year-long infrared rise NEO-wise recorded. Other slow build-up mechanisms could in principle contribute. The grazing reading is the best current fit. It's not yet uniquely determined by the data. So the second stage is suggested by the data, not directly imaged. Now look at what the grazing phase produces visibly. As the planet skims the host's atmosphere, material is shed from both the planet and the disturbed outer layers of the host. Some of that material moves outward. It cools as it expands. Dust forms. The infrared brightness of the system rises gradually over months as more dust accumulates. And this part has a direct anchor measurement. NEO-wise saw the infrared rise. The shape of the climb is in the archive. The duration is roughly a year. The mechanism producing the dust is model-based, but the brightening itself is directly measured, so the brightening is observed. The mechanism is inferred. Now the runaway plunge. The grazing phase eventually crosses a threshold beyond which drag dominates and the orbital decay becomes catastrophic. The planet plunges deeper into the stellar atmosphere on a timescale that's short compared to the previous phases. Mass is shed rapidly. Energy is released. The visible light of the system rises sharply. So this is the optical outburst. The brightening is directly observed. The interpretation that it corresponds to a runaway final plunge is model-based, but it's the natural reading within the in-spiral picture. Now look at the peak and the immediate aftermath. At and just after peak, the strongest transient activity is happening. Material is being thrown out of the system at high speeds. Some of it reaches escape velocity and continues outward. Some remains gravitationally bound and falls back inward. The optical curve fades over the following weeks and months. The infrared, after a brief decline, may continue to evolve as new dust forms from freshly ejected material, so the light curve is directly observed. The layered ejection is inferred from the wreckage geometry that emerges later. Now the long tail. The optical brightness declines gradually over roughly 100 days. During that time, sustained luminosity is supplied by some combination of continued outflow, inflated host envelope contracting back toward equilibrium, and dust reprocessing of light from the central system. Each of these contributions is model-based. The overall duration is directly observed. The exact mix of mechanisms is currently a subject of active modeling. So the duration is firm. The exact powering mix is still under refinement. Now the wreckage Webb saw. By the time Webb observed the system, around 830 days after the optical peak, the immediate transient had long since faded. What remained was a structured aftermath. A small, faint K-type host star at 0.29 solar luminosities directly observed. Warm outer dust at around 720 Kelvin directly observed. Hot inner molecular gas including carbon monoxide directly observed. And here's where the confidence is highest. Each individual measurement is direct. Multiple independent observations constrain the system in different ways. The interpretation of these as remnants of a layered ejection sequence is model-based, but the anchors are firm. Now the ongoing evolution. The dust and gas Webb measured will continue to evolve. The dust will expand and cool. The hot inner gas will eventually relax into the cooler, more diffuse configuration that surrounds the system at large. Over years to decades, the most striking signatures of the event will fade. The system will become harder, optically, to distinguish from a non-disrupted version of the same kind of star. So the future evolution is predicted by the model, not yet observed in detail. Long-term monitoring may reveal it. Now stand back from those 8 stages and look at the picture as a whole. Here's what we observed directly: the optical light curve, the year-long infrared rise from NEOWISE, Webb's measurement of the host star luminosity, Webb's measurement of the dust temperature and structure, and Webb's detection of the molecular gas, including the CO. Those are the anchors. And here's what's model-based: the long pre-event orbital decay, the identification of the grazing phase, the runaway plunge as the source of the optical peak, the multiple mechanism explanation for the long tail, the layered timing of the dust shells. Those are the connecting tissue between the anchors. So this is more carefully grounded than the original 2023 version of the story. The original version had a single dominant model with the host star inferred indirectly. The current version has multiple direct measurements that constrain different aspects of the system, with the model linking them coherently. And that kind of structure, multiple direct anchors connected by physical modeling, is the strongest form of reconstruction the field can offer for an event we can't re-observe in detail. But it isn't a perfect picture. The mass of the destroyed planet isn't pinned down precisely. The exact length of the orbital decay phase is uncertain. The detailed mix of energy sources during the long tail is still under active discussion. The grazing phase is, for now, an interpretation rather than a directly imaged process. Now think briefly about what those uncertainties actually mean for the conclusions. Mass of the destroyed planet is loose because the energy budget can't pin it down without assumptions about conversion efficiency. But the broad mass range, substellar, somewhere between Jupiter and brown dwarf scale, is firm. Length of the orbital decay phase is uncertain because the tidal dissipation properties of K-type stars aren't well measured. But the existence of the decay phase, on a timescale much longer than any active phase of the event, is required by the geometry. The energy mix during the long tail is uncertain because 3 plausible mechanisms can each contribute. But the overall accounting that more than one process is at work is firm. So the uncertainties affect the details, not the headline. The qualitative picture is robust under reasonable variations in any of the specific assumptions. Within those uncertainties, the picture holds together. A planet was destroyed. The destruction proceeded by in-spiral and plunge, not by an expanding host atmosphere. The wreckage records the layered history of the destruction. So the rebuild is structurally complete. We have a coherent narrative anchored in measurements with model-based links that fit the available evidence. We know where the gaps are, we know which parts are firm and which parts are provisional. And that's about as good as forensic transient astronomy gets this far after the event. Now think about what the term forensic actually implies here. Forensic transient astronomy borrows its language from a field where you investigate a one-time event from the evidence it left behind. You don't get to repeat the experiment. You don't get to send the suspect back to commit the crime again under controlled conditions. You work with the evidence on hand, you build the most consistent reconstruction the evidence supports, and you carry forward the appropriate uncertainty. So a forensic reconstruction is, by its nature, a reconstruction of the past from present-day signatures. The signatures are real, the reconstruction is inference, and the quality of the reconstruction depends on how many independent pieces of evidence you have and how well they constrain different aspects of what happened. For ZTF SLRN-2020, we have multiple independent pieces: the optical light curve, the NEOWISE infrared archive, Webb's host star measurement, Webb's dust temperature measurement, Webb's molecular gas measurement. Each of these pins down a different aspect of the system. Together, they constrain the picture much more tightly than any one of them would alone. And here's what makes this kind of multi-anchor reconstruction trustworthy. Each independent measurement uses a different physical principle. The optical light curve uses photometry, straightforward brightness measurement. The NEOWISE archive uses long baseline infrared monitoring. Webb's host star measurement uses spectroscopic analysis combined with distance estimation. Webb's dust temperature uses radiative equilibrium. Webb's molecular gas uses high-resolution spectroscopy. The fact that these independent methods all converge on a coherent picture of the same event is itself a strong consistency check. Now think about what the field would lose if any one of those pieces were missing. Without the optical light curve, we wouldn't have detected the event at all. Without the NEOWISE archive, we wouldn't know about the year-long lead-up. Without Webb's host star measurement, we'd still be defending the original red giant story. Without Webb's wreckage measurements, we'd have no way to test the new mechanism. Each piece carries a specific kind of constraint, and the combination is what makes the reconstruction credible. So the forensic reconstruction we have for ZTF SLRN-2020 isn't just one team's preferred reading. It's the reading that fits all the available evidence simultaneously. That's a stronger claim than fitting any single observation. What this whole reconstruction changes about how we understand planetary death, more broadly, is the broader question we end on. Now stand back from the specific event. What does the ZTF SLRN-2020 story change about how we think about planetary engulfment more broadly? A few things. None of them are revolutionary. All of them are real. Look at the first thing it changes. The basic existence of planetary engulfment as an observed phenomenon is now strengthened, not weakened, by what Webb showed. We've directly seen evidence that a giant planet was destroyed by interaction with its host star. The mechanism turned out to be different from the cleanest version of the prediction. But the underlying claim that planets can be destroyed by their stars survives. So the headline that planetary engulfment has now been observed is still right. The headline that it happens specifically through the textbook red giant swelling and swallowing scenario is, for this case, no longer right. Now think about the second thing. We've learnt that the simplest version of the engulfment story, the version that runs in introductory astronomy classes, doesn't always apply. There's another route, orbital decay, leading to inspiral, leading to plunge, that doesn't require the host star to be near the end of its life. That route can operate around stars at various stages of evolution, including stars still close to the main sequence. So the population of expected engulfment events looks different now. They're not all aged star eats close in planet stories. Some of them, possibly many of them, are decaying orbit meets still young host stories. The events have different host populations, different timescales, different signatures. Look at the third lesson, which is methodological. The 2023 announcement of ZTF SLRN-2020 was based on data that strongly suggested an engulfment but couldn't fully constrain the host. Webb provided the constraint. The constraint, when it arrived, broke the central mechanism of the original picture and forced a rebuild. So we should be cautious about how confidently we settle on any specific interpretation of a transient event before the remnant star can be measured directly. The remnant measurement in events like this is the most decisive piece of evidence available. Until it's in hand, the interpretation is provisional. That's a discipline worth applying to future cases. Look at the fourth lesson about what's coming next. The VRC, Rubin Observatory in Chile, with its legacy survey of space and time, is starting to scan the entire visible sky every few nights. Its sensitivity, cadence, and depth will produce a flood of transient detections far beyond what current surveys generate. Within that flood, planetary engulfment events should appear. How many? Estimates vary, but based on the inferred rate of close-in giant planet in spiral and the sensitivity Rubin will reach, the count could easily climb into the dozens per year, possibly more. Now think about what dozens of events per year actually means for the science. With a single event like ZTF SLRN-2020, we have to argue from first principles about what the typical case looks like. With dozens, we can build distributions. We can ask whether host stars cluster around K-types or G-types or M-types. We can ask whether the year-long infrared lead-up is universal or just a feature of this particular event. We can ask whether the long optical tail is typical or unusual. Each new event becomes a data point in a much broader picture. So Rubin doesn't just confirm individual events, it transforms our ability to characterize the whole class. So the era of single, hard-to-interpret events like ZTF SLRN-2020 is ending. We're entering an era of population statistics. We'll be able to look at not just one event, but at distributions. Distributions of luminosities, distributions of host star types, distributions of infrared lead times, distributions of dust signatures. Now think about what those distributions will tell us. If most engulfments occur around aged stars in the giant phase, we'll see a peak in the host distribution at giant star luminosities. If most occur around still young main sequence stars by the orbital decay route, the peak will sit at much lower luminosities. The distribution itself, taken across many events, will tell us which mechanism dominates. ZTF SLRN-2020 is now a single data point in that distribution. Its host turned out to be a small near-main sequence star, and that's one. We don't know if it's the typical case or an outlier until we have many more. So in some sense, this rebuild is preparation for a much larger investigation. The work we've done in carefully reconstructing what really happened to ZTF SLRN-2020 sets up the framework for analyzing the next dozens of events. We know what to look for, we know which measurements matter, we know how the interpretation chain can break. Look at the fifth lesson, the broader one. ZTF SLRN-2020 reminds us that the cleanest version of a story isn't always the version the data supports. The cleanest version is satisfying, it travels well, it fits the diagrams in textbooks, it confirms long-held expectations. But the cleanest version is sometimes wrong in ways that only better instruments can reveal. So we have to hold the cleanest version provisionally. We have to be willing to update when better data arrives. We have to be willing to say in public when an earlier announcement turns out to be incomplete. Now look at how the field has actually responded. The 2023 announcement was published in Nature. It got widespread press. The diagram of an expanding red giant ran everywhere. When Webb's measurements forced a revision, the revision was published in subsequent papers, less prominently but completely. The technical literature updated. The press largely didn't. So if you go searching for ZTF SLRN-2020 today, you'll find a mixture of articles. Some still describe it as a red giant eating a planet. Some include the Webb correction. The story, in public memory, hasn't fully caught up with the technical understanding. That gap is itself worth understanding. It tells us something about how science gets communicated. The first version of a finding tends to dominate the public memory long after specialists have moved on. The corrections that follow are quieter, more technical, and harder to summarize in a headline. Now think about why the corrections travel less well than the original announcements. The first announcement of a major finding has a built-in narrative structure. For the first time, we've seen X. That's compelling. It suggests progress. It rewards the click. The corrections, by contrast, are usually framed as it turns out to be more complicated than first thought. That's a less satisfying headline. It doesn't have the punch of the original. So even when the technical literature has fully absorbed the correction, the public version of the story tends to remain anchored to the cleanest first telling. So the asymmetry between announcement and correction is built into how science news gets read. We can't blame any particular outlet for it, but we can be aware of the pattern and account for it when we read about new scientific findings. The first version of a story, especially when it confirms a long-held expectation, deserves a little more skepticism than it typically gets. ZTF SLRN-2020 is, on that reading, a lesson in how scientific stories evolve. The first version was the satisfying one. The second version is the one the data actually supports. Both versions involve a planet being destroyed. Both involve a real measurement of an actual event. The difference is in the geometry of the destruction and in what kind of star was the agent of it. Now think about what this kind of revision says about the field as a whole. Astronomy has a long tradition of correcting earlier interpretations as better instruments come online. Galaxies that were once classified as nebulae turned out to be other Milky Ways. Pulsars, when first detected, were tentatively flagged as possible alien signals before their natural origin was understood. The cosmic microwave background was found accidentally and only later recognized as the leftover glow of the early universe. Each of these corrections came with public communication challenges. Each forced reframing of stories that had already begun to spread. So ZTF SLRN-2020 is a recent entry in a long tradition of astronomical updates. The first version was satisfying and traveled fast. The second version is more carefully grounded and requires more nuance to communicate. Both versions serve different purposes. The first is the version that made the science newsworthy. The second is the version that's actually right. So here's where the broader picture lands. We now have direct evidence for a giant planet destroyed around its host star, and a strong model-backed case that this one was driven by orbital decay rather than stellar expansion. We have a worked example of how careful follow-up observations can reshape an early interpretation, and we have a framework for analyzing the dozens of similar events that should arrive in the next decade. That's what's actually changed. The textbook diagram of a red giant eating a planet is still useful for the long-term picture of solar system evolution. The fate of close-in planets around aging stars is still, broadly, what the diagram shows. But the immediate observational situation, the population of events we'll detect with current and upcoming surveys, looks more nuanced, more routes, more host types, more signatures to learn how to read. And ZTF SLRN-2020, the event that started this whole conversation, ends up as a careful first example. Not the simple confirmation it was originally taken to be, a more layered, more interesting case study, one whose lessons will shape how the next dozens of events are analyzed. Now think about what this means for the broader trajectory of the field. Planetary engulfment, as a category, is becoming an observational science rather than a theoretical prediction. We're moving from arguing about whether such events happen to arguing about how often they happen and which mechanisms dominate. That's a meaningful shift. It puts the field in the same kind of position that supernova studies were in a century ago, when systematic surveys started building up large enough samples to ask population-level questions. So the next decade or two of engulfment science is likely to look quantitatively different from the past. Larger samples, better instruments, more careful analysis chains, broader populations of host stars and destroyed objects. Models tested against statistics, not just individual cases. ZTF SLRN-2020 is the first careful entry in that emerging catalogue. Now we can finally come back to the question we started with and answer it. So what really happened to the planet around ZTF SLRN-2020? A giant planet, somewhere between Jupiter mass and a few tens of Jupiter masses, was destroyed by interaction with its host star. That part of the original headline was right. But the way it died wasn't the way the headline described. The host wasn't a swollen red giant reaching out to swallow a close-in world. The host was a small, near-main sequence K-type star, much like the kind of star that sits quietly through most of its life. The planet wasn't overtaken by an expanding atmosphere. The planet fell in. Its orbit decayed slowly, over millions to billions of years, through tidal interaction with the host. It crossed into the star's outer layers. It grazed the upper atmosphere for about a year, shedding material that became the warm dust we see now. Then drag took over, the orbit collapsed. The planet plunged. The system flashed. The flash faded over 100 days, powered by some combination of continued outflow, an inflated stellar envelope contracting back to equilibrium, and dust reprocessing radiation from the central source. Webb, looking at the system more than 2 years later, saw the small remnant-star. It saw warm dust at around 720 Kelvin. It saw hot intermolecular gas including carbon monoxide, the freshest piece of the wreckage, and those direct measurements are what broke the original story. Not because the original story was sloppy, because the original story rested on a host star assumption that hadn't been measured directly. When Webb measured it, the assumption failed, and the model that depended on it had to be replaced with one that fit the same wreckage with a different geometry. The geometry reverses in the new picture. The star doesn't reach out to the planet falls into the star. Same destruction, opposite direction. That's the answer to what really destroyed the planet, and the answer to why the first explanation didn't survive its first real test is in the end simpler than it might have looked. The first explanation had a single critical assumption and a single critical piece of evidence that could test it. Until that piece of evidence existed, the explanation was provisional. When the evidence arrived, the explanation broke. Better instruments produced a measurement that the original story couldn't accommodate. The story changed. That's how science is supposed to work. Even when the cleanest version of a story has already traveled the world, ZTF SLRN-2020 is a single data point in what's about to become a much larger sample. The Vera Rubin Observatory and the next generation of transient surveys will catch many more events like it. Some will turn out to be classic engulfments by aged stars. Some will turn out to be in spirals into stars, still close to the main sequence. The distribution itself, taken across dozens or hundreds of events, will tell us which kind of planetary destruction is more common. The science of how planets die, really die, in the moment of being absorbed into their stars, is in some sense just beginning. ZTF SLRN-2020 is the first careful case study, not the last word. What that says about our own solar system and the eventual fates of Mercury and Venus and possibly Earth is a story for another time. The textbook picture of solar system endings may need its own careful re-examination as the population of observed engulfment events grows. For now, what we have is one event, carefully measured, rebuilt, honestly described. A planet ended around a small star. The star kept going. Wreckage remains.